talk about molecular geometry, we're talking about the shape of an atom, okay, or the arrangement of atoms in a molecule. Okay, there's a couple different things that we have to look at in order to study a compound's molecular geometry. One of which of those things that we have to know is called the electron domains. We have to study and be able to determine how many electron domains a central atom has, okay? And it's kind of important for us to understand we're only studying what's happening around the central atom. So can someone give me, what do I mean when I say the central atom?
Middle.
The middle, right? The atom that's in the middle. So when I study the central atom, I'm looking for what types of things are surrounding it, or what's called an electron domain, right? Domain is like an area, right? So I'm looking about these different electron areas. So there's two types of electron domains. There are bonding domains and there are non-bonding domains. Okay, and a bonding domain just means that it contains at least a single bond. Okay, but a bonding domain could contain a double bond or a triple bond as well. Okay, and it would still only count as a single domain. So we'll look at these in real life here in just a second, but it contains at least a single bond. It could be a double bond or it could be a triple bond. A non-bonding domain contains a lone pair. So just a single one, a single lone pair. And what does that vocabulary word, lone pair, what does that mean? Two electrons that are not in a bond, right? A lone pair is electrons that are left alone, but as a pair, okay? So when we talk about domains, we're looking at both bonding and non-bonding, and we're trying to figure out what are we really looking at here in order to determine its shape. So I want you to take out the chart that I gave you. I want you to look at it just a second, and we're going to determine how do we read this chart, okay? How do we read this chart? And the thing that we have to do first, when we want to determine the molecular geometry of an atom is we find out how many total domains, total electron domains are surrounding the central atom. That's first, okay? See how this column right here says total domains? Okay, that would be the sum of the bonding and non-bonding domains. So we find out how many total things are surrounding the central atom. And let's say, for example, that we find out our atom has 4 total domains. And 2 of those domains are lone pairs, okay, or non-bonding domains. I come down and find the intersection of those 2 things, and I would find out my molecule is bent. Do you see how that works? You find out how many total domains, and if any of those contain lone pairs, or if they don't. Does that make sense? Yes? No? Are we seeing where those intersect? We're looking at what shape that could be. Okay, so that's what we're looking at. So let me give you an example here of a molecule. Okay, let's say that I have COH, and I have a molecule that looks like this. And I wanted to determine the molecular geometry of this molecule. The first thing I have to do is find out how many total domains does this object have. Okay, what do you think? 6. Okay, what makes you think 6?
There's 4 bonds and 2 lone pairs.
Okay, so you're counting 1. Oops. We're counting, if you say 6, we're doing 1, 2, 3, 4, 5, 6. Okay, that's going to be too many, but that's okay. Because why is that too many? We're only looking on the central atom. We're only paying attention to the central atom. So, that's okay. Not yet, but almost. 1, 2, and this is still a single domain, even though it contains a double bond. Okay, it's leading us to one other thing. It's leading us to an oxygen, so it still counts as a single domain. not a double. They're single. So this one, if we look at it, has 3 total domains.
Is that bands as well?
3 total domains. So I'm going to look at my objects and say 3 total domains. Does my central atom have any lone pairs on it?
Yes.
Carbon does not. Carbon does not have any lone pairs. So I'm going to go 3 domains, 0 lone pairs, and that becomes trigonal planar. Trigonal planar. Okay, that's how I find the shape of my molecule. I find the intersection of that chart and figure out where I'm at. So I have 3 total domains, and none of those contain lone pairs, which means I'm trigonal planar. Does that kind of make sense how that works? We're going to do a lot more examples, but I want to give you kind of an overview of how we use this chart. Okay? All right, we'll do some more examples as we go, but let's look at the next one, okay? The reason we do this, or the reason we follow this method of molecular geometries, is due to this theory I call it Vesper theory. I know that's not what the acronym really says, but I call it Vesper theory. And I want you to know this acronym, okay? I need you to know, this is one of the rare things I ask you to memorize, but I want you to memorize this acronym, okay? VSEPR. VSEPR. Stands for valence shell electron pair repulsion theory. Vesper theory is what I call it. Okay? So I want you to write down that acronym right now because that's something that I'm going to ask you to memorize. It stands for valence shell. What does that tell me about the electrons that we're dealing with? Are we dealing with the inner electrons or the outer electrons? The outer electrons. The valence shell electrons are the ones, the outermost electrons available for bonding. So, how many valence electrons does phosphorus have? 5. 1, 2, 3, 4. It's in group 5. It has 5 valence electrons. Those are its valence shell electrons. So when we talk about Vesper theory, we're only concerned with the outer shell electrons. Valence shell, electron pair. What's that mean? How many electrons? 2. An electron pair. That pair can either be the bond between 2 atoms, or it can be the lone pair. Both of those contain 2 electrons, don't they? A bond contains 2 electrons, and a lone pair contains 2 electrons. So valence shell, electron pair. That means we're looking at the outermost electrons that are either contained in a bond or in a lone pair. Are we on the same page so far? Repulsion, what's that mean?
Explosion.
No, it doesn't. What's repulsion mean?
Push away.
Push away, right? Is that what you said, Cito? What'd you say? Yeah, okay. Repel means, to push apart. So, listen. Electrons all have negative charges, don't they? So does negative and negative attract? No, they repel each other. They push apart. So these electrons found within the atom, they want to spread themselves out as far as they possibly can. So based on the number of bonds or number of lone pairs around a central atom, these atoms and these bonds and these lone pairs arrange themselves to give themselves essentially the most space they can. And sometimes they can be as far apart as 180 degrees, right? That's as far apart as you can get. Or they have to kind of move and orient themselves in different ways. So the angles that you see here on your molecular geometry chart, that tells you exactly how far apart those electrons are, whether it's in a bond or whether it's in a lone pair. Okay? This chart is one that you'll always be able to use. Okay, you'll always have this one to use for you. So I'm not going to ask you to memorize any of that, but you do need to memorize the acronym. Valence shell electron pair repulsion. I'm telling you right now, that question will be on the test. Okay? 2 weeks, 2.5 weeks. I don't know. Week and a half, somewhere in that range. I'm not exactly sure. I can look. All right, let's try one here. I've got the Lewis structure for what molecule? This is a Lewis structure for water. So how many electron domains does the central atom have?
4.
It has 4. 1, 2, 3, 4. How many of them are bonding domains? 2 of them are bonding, and how many of them are non-bonding domains? 2. But that's not exactly how we go read our chart, is it? Our chart, we want to know total electron domains. So we're going to look down here at 4 total electron domains. 2 of those of which are lone pairs. So what shape is this? Bent. Right? And that's exactly what it looks like in 3 dimensions. It's not a hydrogen out to each side. Sometimes when we've drawn water in the past, we've drawn it like this. Right? Do you kind of remember drawing it maybe and looking something like that? That's fine, but it's not a 3-dimensional representation of what the molecule actually looks like. What the molecule looks like is this, right? It looks like this top one. These hydrogens are bent down because the lone pairs need their space, essentially, right? And so that's kind of what that looks like. Okay, that's called bent. All right, let's try this one. What's the Lewis structure for BCl3? Let's go ahead and draw that Lewis structure on your notes sheet real quick, and then we're going to look at using Vesper theory to determine our molecular geometry. Okay, so let's start with our Lewis structure first.
B is 3. 3.
Oh, shoot.
3. No, 5, 6, 7, 7, 7, 24.
I think we need 24 electrons. Would you agree?
Yeah. Now what do we do? Using
We're going to draw our Lewis structure first, because that helps us look at electron domains.
Wasn't there something like this on quiz?
Oh, CCl4.
Yeah.
So I've used up all 24 of my electrons. All of my outer chlorines, are they happy?
Yes.
Right? Each of these guys have exactly what they like, but boron does not have a complete octet. Is that okay?
Don't they have 3?
It is okay, actually, for this one. Boron is one of our exceptions to the octet rule. And the reason it's an exception is because, remember, we said boron only contributes 3 electrons.
Yeah.
So it's okay only having 3 bonds, right? It would cause tension if we were going to give it another electron. We could double bond one of those chlorines, but it's unnecessary because then that puts a charge on each of them, which we don't want. Okay, so it's an exception to the octet rule, which means it's okay. So here's our correct Lewis structure. How many total domains do we see on boron? 3. 1, 2, 3. And so I'm going to look at my structure here, or my chart, and I'm going to say it has 3 total domains. Does it have any lone pairs?
No.
No. So this means it would be,
Trigonal planar.
yep, trigonal planar. You can say trigonal. It doesn't make a difference. The pronunciation doesn't matter. But it's basically a big triangle, right? It's making a triangle. There are 3 things around the outside. It's making a triangle. And when it says planar, what do you think that means?
Plane.
Agreed. It's all in the same plane. So it's not moving 3-dimensionally really at all. It's like just this big flat triangle. That's what it looks like. That is enough space. It's 120 degrees. You can't spread out 3 things farther than that, right? It doesn't need to move up or down because it's as far apart as it needs to be right now. So that's, anytime you see the word planar, which there's another one, square, planar down at the bottom, that means all of those atoms are within the same plane. So it's just like a big flat plane. Okay, let's try this one. Why don't we try CBr4? CBr4. All right, here's our skeleton. Let's go ahead and put in our electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. And I think that's how many electrons we needed, was 32. Don't you love when the Lewis structure just works out nicely like that the first time?
But no carbon need what they do it for.
Mm-hmm.
They're finished.
Yeah, I think we're finished, right? It's nice and easy. All of my atoms are happy. They have their preference even, so we're good to go there. So if I'm looking at my if I'm looking at my domains, carbon has 1, 2, 3, 4 domains.
So it's 7.
Tetrahedral.
Good. Tetrahedral. Tetrahedral. What does that prefix tetra mean?
4.
4. Yeah. So that's where we get that word from. Tetrahedral means we have 4 bonds and everything's nice and pretty. Right? 4 bonds. Can you make a prediction on the next one? CH2Cl2?
It's
gonna be a resonance.
No, I don't think it'll have to have resonance. Nope, I don't think it'll have resonance. But can you take a prediction on the shape? CH2Cl2. What do we think? Do you think the shape will also be tetrahedral? I think it will.
What?
Because if I have my electrons here, let's count them. Let's just do it, I guess. CH2Cl2. This is 4 plus 2 plus 14. So it's how many electrons? 20. So that gives me 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Isn't everybody happy there?
No.
Why not?
Oh, yeah, it is.
Because what can hydrogen have?
1.
Only one bond. Hydrogen does not get a double bond. It doesn't get extra electrons. I don't have any extra electrons anyway. But doesn't carbon here look the same?
So
It's just 4 bonds, right? So it's also tetrahedral.
That's what it said. 2. I said 12 on the page.
Oh, sorry. Oh, I see what you're saying. You thought this was C12. That's my fault. No, Cl2. Yep. CH2Cl2. So they're all bonded to that carbon. We have 4 single bonds there. That makes tetrahedral. So 4 single bonds gives us a tetrahedral molecule. Okay? And that means everything's nice and simple. Look at your the 3-dimensional shape of that on your page. Right? What that looks like is kind of like a little pyramid base. And then you've got one atom that's pulling the central atom up a little bit. So it makes this, yeah, kind of this tall triangle, kind of a pyramid type shape. Okay? But we'll look at that in 3D a little bit later. Okay. So if we have lone pairs on the central atom, we call these non-bonding domains. I actually don't need you to write down any of this stuff on this slide. We've already kind of talked through this part. So let's just jump in with an example. We're going to jump in with the example of NH3. I don't need you to necessarily write any of that down. I just want you to write down this example, NH3. Okay? We have to understand that lone pairs take up space just like bonds do. So they still want to move around and get their own space. Okay? They still have to be given room. Okay? So NH3 is 5 plus 3 is 8 electrons. Let me sidestep for just a second. If we draw our electrons in, that's 2, 4, 6. Where do my last 2 electrons need to go? On N. Like that. This one was on our quiz, wasn't it?
Yes, ma'am.
Very good. So is this what everyone's look like? I hope. Okay. You could put, can I put my lone pair right there?
Yeah.
Yeah? Could I put my lone pair right there? No. All right, not by a bond, just in a space, in a gap. I think so.
No, the H was in there, but the O was there.
I think it was something like that.
Or something.
Maybe it wasn't this one. I don't remember off the top of my head. Okay, that's fine. Okay. So sorry. All right,
But
we're looking at total domains. 4.
4.
1, 2, 3, and the lone pair counts as a domain. So we have 4 total, one of which is a lone pair. Okay, so 1 lone pair. This would be
no, you should keep that.
It
on
has
the board.
3. It has
trigonal
Trigonal pyramid.
pyramid. Yep.
No, you should keep that on the board.
Keep this thing on the board?
Yeah.
This one?
Yeah.
I did.
Like, but you should keep it.
Yeah, I will. I'll keep it up there the whole chapter. I told you that. It was up there during your quiz. Okay. Trigonal pyramid. It actually makes the same shape as tetrahedral, but up on top, you don't have a bond. You just have a lone pair. Okay, so it makes the same kind of shape. It's still 3-dimensional. It's got that kind of shape on it. Okay? On your sheet, I didn't explain this very well, but do you see how on some of these bonds, there's a dark, thick line and a dotted line? You see what that means? The dark, thick line means like there's an atom coming out towards you, And the dotted line means like there's an atom going back in towards the page, kind of, right? It's supposed to be helping you in 3D really visualize where those things are going. So think of it as like a tripod, right? I think that's the best example.
Miss, how can you tell the lone pair?
How do I know where the lone pair goes? You could put it in any gap here.
Yeah,
I could put it here.
I know how you see that you can tell like the total electron domain, and you just go on it.
Oh.
How do you go over that?
Okay, since I have 4 total domains, one of them is a lone pair. I'm going to come up here and say I have 1 lone pair. And then where they meet,
How much the house? One?
this one has 1 because here's on the central atom, there's 1 lone pair. Yeah. All right, what do we do with double bonds? How many domains does a double bond count for? 1. What about a triple bond? DJ, how many domains does a triple bond count for?
a triple bond.
Uh-huh.
A triple bond has
How many domains is it?
3.
Mm.
What? 2.
A triple bond would count for how many domains?
What?
One. Because it's leading us to one thing. A double bond only counts for 1 domain. A single bond counts for 1 domain. It's almost, think of it as how many things is it taking us to? Well, it's just taking us to one other thing, right? So double bonds or triple bonds still only count as 1 domain. You might want to write that down. Multiple bonds leading to 1 atom count as 1 bonding domain. I would write that down. Multiple bonds means 1 domain.
What does a double bond have?
A double bond means 1 domain.
Some is a triple bond.
1.
So what have a different number?
So let's say I have this molecule. But if I look at this molecule right here, how many total domains are on carbon? 1, 2. That's it. 2 domains. So what shape would this molecule be? It would be linear. Linear. 2 total domains, no lone pairs. Right? Those bonds, look, can't you just tell by looking at it? These bonds are 180 degrees apart. It's just, it has to be a straight line, right? It can't orient itself any other way, because if it did this, that would only be 90 degrees, right? That wouldn't be far enough away. They want to be as far away as they can be. So it has to be just like a straight line, right? It has to be linear. Okay, so 2 domains there. Okay, you might want to write this out. We did this example, 2 domains. Right? Even though there's a triple bond there, it still only counts as 2 domains. Yeah. On which one? On carbon? Oh, okay. You're only looking at central atom. We don't care about nitrogen because it's not in the center. Yeah, good question. Yep. So Jacob asked, well, isn't there a lone pair there? Yes, but it's not on the central atom, so we don't have to count for that.
What the bottom piece is?
This is just a no good example. That's showing you a wrong example.
Oh.
We can't have it like that because our electrons are too close together, right? They want to be even farther apart. Okay. Let's try one for carbon dioxide. Now you have to even tell me what's the formula for carbon dioxide. What is it?
CO2.
CO2. Okay, CO2. So carbon gives us 4. Oxygen each gives us 6. That means we need 16 electrons.
So put C and 2 on both sides.
C and oxygen on both sides, agreed. CO.
Then put a triple bond.
A triple bond.
No.
So I'm going to bond each. That's 2, 4, 6, 8, 10, 12, 14, 16. There's all my electrons. I've got them all on there.
But don't make carbon need 4 bonds?
That does. So what can I do to help that?
You can do a double bond on both sides.
Okay, good. I can double bond on both sides, which means I'm going to remove a lone pair from each oxygen
Double bond.
into a double bond.
Way to go, Doc.
Does this structure need resonance?
No.
No, because it's symmetrical and I didn't make a choice, right? I did it on both sides. So this is a correct Lewis structure because all my elements are happy. But what is the molecular geometry?
Linear.
Linear, right? Here is 2 domains. none of which contain lone pairs. So 2 total domains, no lone pairs, tells me it is linear. So try this one on your own. Phosphorus trichloride. You got to figure out what is the formula first. Then.
Is it a PCl3?
I don't know.
I think,
Phosphorus trichloride.
but I don't have a thing on though. I have 26 volumes left in my P. My P need my P don't have no.
Then I think you go count your electrons again. Have you already used all 26?
Yeah. Hold on, let me see. 2, 4. Oh, I got it. Now I get it.
Did you figure out I want you to figure out the shape.
I got the big blue. Think it's a. Right?
Ready?
Yes, ma'am.
ASF5. So arsenic. Arsenic, what would we call it?
5
Arsenic.
plus.
What would the name of our molecule be? ASF5.
ASF.
Arsenic.
Fluoride. Fluoride.
Penta. Arsenic pentafluoride. I know that's what you guys were all going to say.
Way to go, see those.
Nope, you'll get it. Okay.
Are we gonna play